Hi, Algebra 2 students. This is Ms. Penn. Your notes today are on nth roots and rational exponents. And what we saw today in class was that rational exponents or exponents that have fractions are related to roots. And so first thing we're going to do is kind of review what is a root. So the roots you're most familiar with are square roots. So if I say just the square root of 9, that means what number raised to the second power is 9. So I know that the square root of 9 is 3 because 3 raised to the second power is 9, right? Now technically there's another root which would be -3 because -3 squared is also 9. So we know that there's this relationship between exponents and roots, right? And then this is a square root, but then we also are going to start looking at other kinds of roots. So like we could have a cubed root of a number. So like the cubed root of 8 means what number raised to the third power is equal to 8. So I could start thinking, oh, well, what about 2? Because 2 times 2 is 4, times another 2 would give me 8. So that means 2 to the third power is 8, right? So these kind of like exponential relationships go hand in hand with the roots. And then if we want to generalize this, we could say that the nth root of the nth root of A is equal to B. So A and B are numbers. Well, that is going to mean that B raised to the n power, right? B raised to the nth power is equal to A. And just for like, in terms of when you talk about this, we'd say the nth root of A is B. So let's now kind of get into how do the roots relate to rational exponents. Okay, so this is getting at the exploration that we did in class today, right? Which showed that x to the 1/2 is doing the same thing as the square root of x, right? So if we wanted to generalize that, we could say, we're going to keep using this same like letter notation, so we're always going to have an a for the number inside the root. So we say the nth root of a is equivalent to a to the 1/n. So whatever the root was here, that becomes the denominator of your exponent in rational exponent form. Okay? Now, sometimes what you'll see is you'll have an nth root of something, but you might have like an exponent inside. So like the nth root of a to the m. And what we're going to see there is something interesting. Well, that n is still going to become the denominator of our fraction. But we already were raising a to the mth power, so that stays there. So it becomes a to the m over n. Okay? So we are going to kind of use both of these when we kind of convert. So like if you guys could actually, if you pause the video to kind of make this chart, then we're going to try to fill in how do we convert from a radical or a root form into a rational exponent form, and then vice versa going back. So I would pause the video for a moment, create this chart, and then you can press play to see the examples. Okay? So let's start with the first example. We have the square root of 9, right? So remember, if you don't see any number, we're assuming it's a square root. So the square root of 9, that means if I was going to write that as a rational exponent, I would do 9 raised to the power of 1/2, or 1/2. Okay? For the next one, it's the fourth root of 81, so that would be 81 raised to the 1/4 power. The third root of -27, -27 raised to the 1/3 power. Now, this would be an example. We have the fourth root of x to the third. This is an example that we're going to need to have a denominator and a numerator for our fraction. So the key is that like whatever the like normal whole number exponent is, it stays where it is. So I'm still going to have like an x to the third. But then this the root 4 becomes a 1/4 exponent, right? And then we can realize, oh, if I just use my multiplying fractions rule, that's equivalent to x to the 3/4. Okay, so the next 3 examples are going back the other way. So if I give you a rational exponent, can you convert it into the root or the radical form? So here, the first one, we have 25 raised to the 1/3 power. So that means the cubed root of 25. So what was in the denominator of my exponent is now the root. So the next one would be negative 3x to the 5th root, or the 5th root of negative 3x. Okay, and then the last one is one of those ones where I have to deal with a denominator and a numerator in my rational root. So the idea is I could separate it, right? So I could say this is the same thing as y minus 5 to the 3rd, and then times like the 1/5. So what that means is that would make this the 5th root of y minus 5 to the 3rd power. So notice that the exponent of 3 never moved. It stayed where it was. The only thing we kind of pulled out from the original rational exponent was the denominator, which became the root. For the next part of your notes, we're going to investigate the difference between taking an odd versus an even root. So odd versus even roots mean like your end value. So this, like, the square root is an even root, but the cubed root is odd because 3 is odd, the 4th root is even, etc. And so the way we're going to do this is by first looking at powers of 2 and powers of negative 2, and it's going to help us establish some patterns here. So the idea, if we you could kind of pause again and write down all of these powers and then roots, and then we're going to fill them out together. So 2 squared, that's easy. I'm going to go through this pretty quick because you should be good on this. So 2 squared is 2 times 2, which is 4. 2 to the 3rd is 2 times 2 times 2, which is 8. Then I have 2 times 2 times 2 times 2. There's a reason that I'm actually writing out all my 2s. So please write out all your 2s, even though it's kind of annoying or tedious. So I get 16 there, and then with 5 2s, that's going to be like 1 additional 2 than I had here. So that'd be 32, right? So now I'm going to do the same thing with the negative bases. So negative 2 times negative 2 is equal to positive 4, right? So notice that negative 2 squared, we get the same thing as we get with positive 2 squared. So next up, we have negative 2 to the 3rd, so that'd be negative 2 times negative 2 times negative 2. So that's the negative 2 times negative 2 is positive 4 times another negative 2 would be negative 8. So notice here, I have a different solution than I did here for my to the 3rd powers. I get negative 8 instead of positive 8. So now to the 4th power, negative 2 times negative 2 times negative 2 times negative 2. So we could kind of group them and say, oh, negative 2 times negative 2 is positive 4. And then this negative 2 times this negative 2 is also positive 4. So this has got to be positive 16. Notice again, these match, right? So 2 to the 4th is 16, and negative 2 to the 4th is also 16. With my negative 2 to the 5th, it's like times 1 more negative 2. So it's going to be 16 times negative 2, which would be negative 32. Okay, so notice here we get a negative 32, but here we get the positive 32. Okay, so now we're going to take a look at taking some roots, and we should be able to find all of our answers somewhere over here. Okay, so when I think about what is the square root of 4, well, that's pretty easy for us to do, but when we look over here, we know that 2 squared is 4, but also negative 2 squared is 4, so I get 2 and negative 2. For the cubed root of 8, well, I know that 2 to the 3rd power is 8, so that's definitely going to be a solution. Is there another number raised to the 3rd power that is 8? Well, not negative 2, because that equals negative 8, so it's just 2. For the 4th root of 16, I'm going to get the 2 to the 4th equals 16, so I get 2, but I also get, down here, negative 2, right? the fifth root of 32, positive 32 only shows up once, right? So it's just 2. So that kind of takes care of all of the positive a values, right, that we kind of saw show up over here. So now the next 4 roots are with the negative a values. So we start with negative 4. How do we get negative 4? Can we take the square root of negative 4? Well, we know from our complex numbers unit that would be an imaginary number, right? So all I'm going to write for right here is just no real root. We know that it would be plus or minus 2i, but for these purposes, we're just going to say no real root. We might get to some dealing with i's later, but for now, we're not going to worry about I. The cubed root of negative 8 means what number times itself 3 times is negative 8? Well, I see that is negative 2. And then the fourth root of negative 16, again, I run into a problem because no number raised to the 4th power is negative 16, because negative 2 to the 4th is positive 16, right? So we'd say, again, this would be an example where you'd get some i's involved. So we're just going to say no real root, okay? The last one is the fifth root of negative 32, and we see that negative 32 is negative 2 to the 5th power. So it's only negative 2. Okay, so I don't know if you notice, but the only times we get 2 roots, right, are with the square root of 4 and the 4th root of 16. Every other time we're just getting one positive or one negative. Okay, so this is going to lead us to try to come up with some generalizations about what types of roots can we get when we're square rooting or cubed rooting or 4th rooting, and it depends on if it's odd or even. Okay, so you could pause and kind of copy down this little chart situation here. But the idea would be, so we're going to kind of separate it into the cases where n is even or n is odd. So if n is even, that means, let's just remind ourselves, n is the root, right? A is the number inside the root. So if n is even, like 2 with the square root of 4, or 4, the square root of 16, then if a is less than 0, that means if a is negative, just kind of writing that for our notes, what happens if we have an even root? Well, there was 2 times where we had a negative. We had a negative right here with the square root of negative 4. I'm sorry, there's 2 times where a is negative and n is even. So we have the square root of negative 4, and we saw we got no real roots. Or we had the 4th root of negative 16, and we also got no real roots. So anytime your root is even, you're not going to be able to get an even root of a negative number. So it will always be no real roots here. All right? When your a value is 0, so imagine you just have like a 0 in here, well, any root, like 0 raised to any power is still 0, right? So you're always going to get 0 if a is 0. So we just say 1 real root, which is equal to 0. And now the last case is where a is greater than 0. That means a is positive. So if a is positive and n is even, we have the square root of 4, the 4th root is 16, we get the positive and the negative solutions, right? So for even roots, that's what we're going to get. Sometimes we're going to have 2 real solutions because both the positive and the negative will work. So I was going to write solutions. I'm going to change that to say roots, so I'm consistent. Okay, now let's think about the same kind of idea, but for when n is odd. Okay, so when n is odd and a is less than 0, that means a is negative. So we can kind of look at like the cubed root of negative 8 or the 5th root of negative 32. And we actually were able to get solutions there. It's not the same as when you're square rooting a negative. So with evens, you can't take an even root of a negative number. Odds, we see that we can, but it only gives us one answer, right? We're not getting 2 different answers. Actually, that's the case also when a is positive. When a is positive, we have the cubed root of 8 and the fifth root of 32, we only get one answer, the positive answer, right? So the idea is here, if n is odd, we're always only going to have one root, not two, because when a is 0, we'll also still get a root, which is 0. So for all of these, we're going to just say there is one real root. Okay? And like, this isn't necessarily, it's not always going to help you, but it's kind of like a good conceptual way of approaching problems when you're trying to get a solution or evaluate a root. So if I slide this up, we're going to look at a couple of examples. So if I say, find the nth root of a, and then I give you a value for n and a value for a. That means, okay, it would be easier for me to think about this problem if I wrote it as a root, right? So remember the nth, I'm going to keep writing this, the nth root of a, so that would mean the cubed root of negative 64, right? And I should expect, now again, I have an odd n and a negative a. I'm expecting it to just be one real root, and I should expect it to be something negative, right? Because I'm multiplying something by itself 3 times. So if it turns out to be negative, then that number better be negative to begin with. So I'm thinking what times itself 3 times is 64. The first number that kind of pops into my head to try would be 4 or negative 4. So I think, what is negative 4 times negative 4 times negative 4? Well, this is positive 16 times another negative would be negative 64. So then I know this is equal to negative 4. Looking at the next example, the 6th root of positive 64. So this is a little, even though like we still are using 64, we have a totally different situation. So now I'm doing the 6th root of 64. So now, because a is positive and my root is even, I could get a plus or a minus solution. It could be positive or negative. So I'm wondering what times itself 6 times is 64. And my thought is, well, if the 3rd root of negative 64 was 4, maybe the 6th root of positive 64 is 2. So I could test that out. 2 times 2 times 2 times 2. 1, 2, 3, 4, 5, 6. And based on my work up here, I know that if I just multiply by another 6, another 2, I get 64. So that checks out. So then I know it should be 2. But also, if I made all of these negatives, right, all the pairs of negative numbers would become positive. So I'd also get positive 64. So I need 2 and negative 2. So I'm going to leave you guys this one to try. And then we will be practicing evaluating roots and going back and forth between these two different forms in class tomorrow. Have a good evening.